Salut tout le monde, welcome back to now episode 20 of the Differential Geometry reading streams. I'm Anthony, of course, if you're new. Welcome back, everybody. We are at over 1,000 subscribers now, and I keep forgetting to mention this in the beginning, but I put my website up, which is anthonymakesvideos.com. It's been up for a couple weeks now. I've been forgetting to mention it in these intros, like I said. The website is pretty much perpetually under construction is how it's going to be, but right now it's especially under construction. I mean, it's basically, if I'm being honest, right now it's just copying the link tree style format of organizing my various links across the internet. I want to have the email associated with the website, so it would be anthony@anthonymakesvideos.com. I want to get that to be working. I have everything installed and configured properly, I'm pretty sure, except there are some things where, like, if I email a Gmail server or a Gmail emails that email, it's like somewhere in between those emails are getting disregarded as spam, and so they're not showing up in either place. But I think the actual sending and receiving is going through. Anyways, that shows you the extent of my knowledge of how email servers and stuff work. But, you know, I feel like it's a good exercise to learn about all this stuff. And it's just like Luke Smith, who, if you know about him on YouTube, that guy hasn't posted in quite some time now, but I'm basically following his instructions on how to set up my website and all that. But his philosophy, I think, is correct, which is that in today's day and age, if you have your own website, that's kind of analogous to having your own land back in the day. Because if you're just putting up all of your data and stuff on like Instagram, YouTube, or whatever, you're kind of like a serf who's doing all of this work for the feudal lord. But if you have your own website, then that's where it's like having your own land. So yeah, check that out. I might set up a Patreon. Who knows? I was also trying to freestyle earlier this morning, spit some bars to hopefully have put at the beginning of this video, but obviously it was so bad that I didn't put anything at the beginning of this video. But rest assured, I am working on that. So quick little update on the freestyling. Oh yeah, this might not really mean a whole lot to you guys since you're watching this. And I don't know if you've noticed, but the PDF that I'm reading from, that I'm sort of like screen recording doing this all on, this PDF is missing parts of the book, as we've seen already. So it's missing the preface, it's missing whole chunks of the solutions, and it's missing parts of the collection of formulas, kind of like the formula sheet spread across over a few pages in the back. Some of those pages of the collection of formulas are missing. And as we will see, or as I have found in this chapter here, chapter 6, mappings, there's several pages missing from this chapter. So in the PDF, we are definitely missing pages straight out of the body of the text. But all right, now I'm going to do something that I've also skipped over in the last couple of videos, which is reading viewer comments. Haven't had as much of a diverse grab bag of comments, and I'm not gonna lie, I'm like probably 10 Vanderhagen the Stampede comments behind in just reading them, because Vanderhagen the Stampede's comments are so like well thought out, I feel like, or they're so detailed sometimes that I feel like I have to like really sit down and commit to reading them and really like get the most out of them, because you guys clearly put a lot of time into these comments, so I really appreciate that. It's part of what makes, when I film these every week, it feels like this time is like the closest I get to self-actualization sometimes, and your guys' comments help push me to that point. So I really try to get the most I can out of your guys' comments. So Vanderhagen the Stampede, you always get recognition for the effort you put in the comments section, but the viewer comment of the week award is going to go this week to Kevin Tang 4932. This one's from a few weeks ago. It's on the Christoffel symbols and umbilics video, which, of course, just a side note about the titles of these videos, I feel like whether or not it's like a hard-hitting topic plays a huge role in whether the Google SEO impact of the video will be high or not. So Christoffel symbols and umbilics, I was like, question mark, is this going to turn out or not? And it was actually a decently average video, I would say. But anyways, Kevin Tang 4932 says, this book seems to emphasize working within specific charts or coordinate frames, which is really helpful for physics and computation. I agree. After this book though, I just want to recommend a book like Loring Two's Differential Geometry, which shows the beautiful ways in which differential geometry can be done using differential forms, and where everything can be expressed in a coordinate-free manner without all these coordinate indices on general Riemannian manifolds. A lot of it is going to be the same, except written in a different form. But the nice thing is that with this technology, it allows us to go further and look at generalizations of things like the Gauss-Bonnet theorem to higher dimensions using cohomology. Search up the Chern-Gauss-Bonnet theorem. Love your videos. Thank you, Kevin Tang, for your comment. I will say that I have come to realize these kinds of, like, I don't want to say shortcomings, but just how this differential geometry book could be seen more as like a stepping stone to more serious differential geometry. I've kind of mentioned it before. This is almost like differential geometry for a physicist who wants to get to general relativity, reading the actual mathematics involved as quickly as possible. Sort of kind of how you said that this book is really helpful for physics and computation. But the fact that, for example, it limits a lot of its treatments to specifically three-dimensional space in order to achieve that end means sacrificing some of the rigor as far as not defining a manifold outright. So we only look at like a vague concept of a surface in this book, but we never touch on a manifold. And then, as we'll come to see in this chapter on mappings, we sort of touch on but never get to the actual formal concept of a diffeomorphism. And Kevin Tang mentioned Loring Two's Differential Geometry. I was actually looking at that one, but I also recently picked up Introduction to Smooth Manifolds by John M. Lee. This book is definitely a bit of a monolith, and just as a side note, this is what it looks like to cry into your industry money after leaving academia. Instead of buying used textbooks, you get to buy the new ones, and this one is really just like a crisp, brand new hardcover textbook. It's just something that, you know, you really appreciate. Oh boy. Anyways, but like the concept of a diffeomorphism is right off the bat in chapter 2 of this book, right? And this is, I would say, people would probably agree that this is like a solid standard graduate level differential geometry book. It's not really called differential geometry at this point, you know what I mean? But alongside this, I was also looking at Loring Two's Differential Geometry, as well as, I don't know if it's pronounced Spivak's, Comprehensive Introduction to Differential Geometry. But yeah, I'm definitely going to follow up with Kevin Tang's recommendation, which is another differential geometry text after this one to really round things out. You know, I also talked about the Kuno book before. I have been referring back to that, as well as those MIT OpenCourseWare notes for other chapters, sort of like how in a previous video, after I got done reading the chapter on the theory of curves, I did like a review episode where I read the MIT OpenCourseWare notes. I haven't done that as an actual video since then, but I have been kind of doing that on the side. And so yeah, there's just kind of rounding out my differential geometry stuff here. I don't know, it's been really interesting. So, but thank you for your comment, Kevin Tang 4932. You get the Viewer Comment of the Week award this week. It's hard to believe that here we are in chapter 6 now, which is a little bit beyond halfway through the book. So, feels good, let's keep going. Chapter 6, Mappings. Section 56, Preliminaries. The concept of a mapping was introduced in section 3. Let us now consider a one-to-one mapping u alpha tilde, which is equal to a function h alpha in terms of u1 and u2, where alpha is equal to 1 or 2, of a portion capital S of a surface with coordinates u1 and u2 onto a portion capital S star of a surface with coordinates u1 tilde and u2 tilde. The mapping given by u alpha tilde is said to be an allowable mapping if the functions h alpha are of class R greater than or equal to 1, and if the corresponding Jacobian does not vanish. We may introduce on capital S star new coordinates u1 star and u2 star by using the mapping functions h alpha for a coordinate transformation u1 tilde equal to a function h1 in terms of u1 star and u2 star, and u2 tilde which is equal to a function h2 in terms of u1 star and u2 star. Then the mapping of capital S onto capital S star takes the simple form u1 star equal to u1 and u2 star equal to u2. That is, the values of the coordinates of any image point are the same as those of the corresponding inverse image point. We may briefly say that the coordinate systems on S and S star are the same. In other words, the transformation to coordinates u1 tilde and u2 tilde by functions h1 and h2 respectively introduces the coordinate system on S as coordinate system on S star. Mappings of surfaces were first considered a long time ago, particularly in connection with the problem of constructing maps of the globe for nautical or other purposes. Problems of that kind provided the impetus for much of the development of differential geometry. Several mapping problems were first solved empirically, and the mathematical foundation for them was not developed until much later, for which referred to the remarks on the Mercator projection in section 65. The whole development started with the investigation of special mapping problems by Jacob Bernoulli, who lived from 1654 to 1705, Johann Bernoulli, who lived from 1667 to 1748, Leonard Euler, who lived from 1707 to 1783, Joseph Louis Lagrange, who lived from 1736 to 1813, and Gaspard Monge, who lived from 1746 to 1818, and others. And wow, that last sentence was really deja vu, a flashback to the intro to the last video on geodesics. Anyways, but the development of a systematic theory of mapping is generally considered to have started with the publication of Gauss's paper on conformal mapping. Of particular theoretical and practical interest are mappings which preserve certain geometric properties. The most important type is the isometric or length-preserving mapping, which preserves the lengths of every arc on a surface to be mapped. Further types which we will consider are the conformal or angle-preserving mappings, which preserve the angle between every pair of intersecting curves on a surface, and the equiareal mappings, which preserve the area of any portion of the surface to be mapped. Section 57, isometric mapping, bending, concept of intrinsic geometry on a surface. An allowable mapping of a portion capital S of a surface onto a portion capital S star of a surface is said to be isometric or length-preserving if the length of any arc on capital S star is the same as that of its inverse image on capital S. Necessary and sufficient conditions for a mapping to be isometric are as follows. Theorem 57.1. An allowable mapping of a portion capital S of a surface onto a portion capital S star of a surface is isometric if and only if, at corresponding points of capital S and capital S star, when referred to the same coordinate systems on S and S star for which referred to section 56, the coefficients of the first fundamental forms on capital S and capital S star are the same. That is, G sub alpha beta equals G star sub alpha beta, where alpha equals 1 or 2 and beta equals 1 or 2. The proof is as follows. Let u1, u2, and u1 star and u2 star be the coordinates on capital S and capital S star respectively. Since those coordinate systems are assumed to be the same, the mapping is given by u alpha star, which is equal to u alpha, where alpha equals 1 or 2. If u alpha is equal to a function h alpha in terms of a parameter t, such that t is greater than or equal to 0 and less than or equal to t1, and alpha can be either 1 or 2, so if this u alpha is an arbitrary arc capital C on capital S, then its image, capital C star, can be represented in the form u alpha star equal to a function h alpha of t, where t is greater than or equal to 0 and less than or equal to t1, and where alpha is equal to 1 or 2. And in this case, the function h alpha of t is the same h alpha of t as before. In arc capital C tilde, given by u alpha, which is equal to the function h alpha in terms of t, where t is greater than or equal to 0 and less than or equal to t naught of capital C, has the length s of t naught equal to the integral from 0 to t naught of the square root of g sub alpha beta times h alpha prime times h beta prime dt, where t naught is greater than or equal to 0 and less than or equal to t1, and the corresponding image has the length s star of t naught equal to the integral from 0 to t naught of the square root of g star sub alpha beta times h alpha prime times h beta prime dt, where of course primes indicate derivatives with respect to t. If For every point capital P of capital S and its image capital P star of capital S star, we always have that G sub alpha beta equals G star sub alpha beta, where alpha equals 1 or 2 and beta equals 1 or 2. Then S of T naught equals S star of T naught. Conversely, in order that S of T naught equals S star of T naught hold for every value of T naught, where T naught is greater than or equal to 0 and less than or equal to T1, the integrands of the above integrals must be equal. In order that any arc on capital S star have the same length as that of its inverse image on capital S, the integrands must be equal for any pair of functions h1 of t and h2 of t whatsoever. Consequently, the relation that G sub alpha beta equals G star sub alpha beta, where of course alpha equals 1 or 2 and beta equals 1 or 2, must hold. This completes the proof. Two surfaces, or portions of surfaces, which can be mapped isometrically onto each other are said to be isometric. We come to an example. The cylinder capital S with a vector parametric representation given by x in terms of u1 and u2, which is, entry-wise, cosine of u1, then sine of u1, then u2, can be mapped isometrically onto a strip of the plane with a vector parametric representation x in terms of u1 star and u2 star, which is equal to, entry-wise, u1 star then u2 star then 0. The mapping is given by u1 star equals u1 and u2 star equals u2, where u1 is greater than or equal to 0 and less than 2 pi. Since g sub 1 1 equals g star sub 1 1, which equals 1, and g sub 1 2 equals g star sub 1 2, which equals 0, and g sub 2 2 equals g star sub 2 2, which equals 1, and these are referring to coefficients of the first fundamental forms, which are involved here, the mapping is isometric. It may be visually accomplished by cutting the cylinder along the generating line u1 equals 0, and then bending it until it covers the strip where u1 is greater than or equal to 0 and less than 2 pi of the plane. We now state the following important theorem 57.2. Isometric surfaces have the same Gaussian curvature at corresponding points. Corresponding curves on those surfaces have the same geodesic curvature at corresponding points. The proof is as follows. According to the theorem egregium, which was given in section 46, the Gaussian curvature depends on the coefficients of the first fundamental form only. Those coefficients are invariant under an isometric mapping, for which referred to the previous theorem 57.1. The statement on the geodesic curvature follows similarly from the previous theorem 49.1. Whereas a reminder, theorem 49.1 was that the geodesic curvature kappa sub g of a curve capital C on a surface capital S depends on the first fundamental form of capital S only, and also of course on capital C, which is kind of implied by how this proof was stated just now. In consequence of theorem 57.2, isometric surfaces must necessarily have the same Gaussian curvature at corresponding points, but this condition is, in general, not sufficient. It is sufficient in the case of surfaces of constant Gaussian curvature. For details, see section 91. Furthermore, we note theorem 57.3. Let capital C be an arc of minimum length joining any 2 points P1 and P2 on a surface capital S. If capital S is mapped isometrically onto a surface capital S star, the image capital C star of capital C is an arc of minimum length joining the image points P1 star and P2 star of P1 and P2. The proof is as follows. If capital C star were not an arc of minimum length between P1 star and P2 star, then in a neighborhood of capital C star, there would be an arc shorter than capital C star. The inverse image of that arc would lie in a neighborhood of capital C and would be shorter than capital C since the mapping is isometric. This contradicts our assumption on capital C. We will now explain the fundamental geometric significance of isometric mappings and introduce some concepts related to our previous considerations. A continuous deformation of a surface, or of a portion of it, is called a bending if this deformation preserves the length of every arc on the surface. Surfaces which cannot be bent are said to be rigid. An example of a bending is illustrated by drawings in section 81. Surfaces which can be transformed into each other by bending are also called applicable. Of course, applicable surfaces are also isometric since bending is length preserving by definition. The concepts applicable and isometric are normally used used in the same sense, but applicability is not an immediate consequence of isometry. We mentioned some results concerning local considerations without proof. In the case of surfaces of vanishing Gaussian curvature, the two concepts are identical. Isometric surfaces of negative Gaussian curvature are applicable provided certain conditions of differentiability are satisfied. Analytical isometric surfaces of positive Gaussian curvature either are applicable to each other or one of them is applicable to the image of the other obtained by a reflection in a point or a plane. Properties which remain unchanged under a bending are called bending invariants. Obviously, a property is a bending invariant if it depends on the first fundamental form only, since this form remains unchanged under bending. Examples of bending invariants are the Gaussian and the geodesic curvature. Counterexamples are the mean curvature and the normal curvature, since the latter two quantities also depend on the second fundamental form of a surface. It is of basic importance that there is no difference in the measurement of lengths, angles, and areas on isometric surfaces, although the surfaces, when considered from the embedding space, may have an entirely different geometric shape. In order to characterize this fact more precisely, we call intrinsic or absolute properties of a surface all those which depend on the first fundamental form only, but are independent of the second fundamental form. The totality of the intrinsic properties is said to constitute the intrinsic geometry of a surface. Isometric surfaces have the same intrinsic geometry. Examples were considered in the preceding chapter, further ones will follow. Plane and cylinder furnish a simple, particular example. Portions of the latter are applicable to the plane. Consequently, those surfaces have locally the same intrinsic properties and therefore the same local intrinsic geometry. But the global intrinsic geometries of those surfaces differ essentially from each other. For instance, there's exactly one geodesic, a straight line, through two given points of the plane, but there are in general infinitely many geodesics through 2 points of a cylinder, for which refer to section 50. We recall that we have obtained the first fundamental form of a surface by means of the metric of the embedding Euclidean space. In this sense, the metric of the space induces a metric on a surface. But if the analytic formulae of the length, angle, and area in terms of the coefficients g sub alpha beta of the first fundamental form have been derived, for which refer to sections 35 and 36 previously, then a metric tensor being given, one may use these formulae without considering the surface to be embedded in a space. The embedding becomes unessential. The problem of finding all surfaces applicable to a given one was first investigated by Gauss and later by Bohr, and is known as the problem of Bohr, and also referred to the important contributions to this problem by Bonnet and Kadazi. In the following, we will consider the problem of Bohr for the special case of surfaces of vanishing Gaussian curvature. That is, we will determine all surfaces applicable to a plane. We finally mention theorem 57.4, the theorem of Bohr. For every right helicoid capital S, there exist surfaces of revolution which can be mapped isometrically onto capital S. The following problem is called after Minding. Given two surfaces with given first fundamental forms, find whether there exists an isometric mapping of the one surface onto the other. But now we're going to come to problem 57.1, which is actually to prove the previous theorem of Bohr, or theorem 57.4. We consider a surface of revolution, capital R, with a vector parametric representation given by x in terms of u1 and u2, which entry-wise is u1 times cosine of u2, then u1 times sine of u2, then a function h in terms of u1. Then ds squared is equal to the quantity 1 plus h prime squared closed quantity times du1 squared plus u1 squared times du2 squared. Let capital S be the helicoid to be mapped onto capital R. We introduce on capital S the orthogonal coordinates u1 star and u2 star defined in the answer to the problem 35.1. Then ds star squared is equal to the quantity 1 plus the fraction with the numerator u1 star squared times capital G prime squared over the denominator u1 star squared plus c squared closed quantity times du1 star squared plus nu squared times the quantity u1 star squared plus c squared closed quantity times du2 star squared. We set the following with the associated labels for the ease of recalling these expressions later. We set 2 to be u2 equal to u2 star. We set 3 to be where u1 squared is equal to nu squared times the quantity u1 star squared plus c squared. And we set 4 to be where the quantity 1 plus h prime squared times du1 star squared equals 1 plus the fraction with the numerator u1 star squared times capital G prime squared over the denominator u1 star squared plus c squared. If the right helicoid, that is the function capital G, is given, we obtain from expression 3 expressions for u1 star and du1 du1 star. Inserting these expressions into expression 4 and integrating, we find the function h, that is the meridian of the surface of revolution capital R, which can be mapped isometrically onto capital S. If capital R is given, the corresponding isometric right helicoid can be determined in a similar manner. The isometric mapping is given by expressions 2 and 3. Since in the above expressions the constant nu, as well as the constant of integration, may be arbitrarily chosen, for any given right helicoid there exist infinitely many isometric surfaces of revolution and vice versa. It follows from expressions 2 and 3 that the images of the parallels where u1 is equal to a constant of the surface of revolution are the helices where u1 star is equal to a constant. An example of this mapping will be considered in problem 81.1. And we're going to keep this one short today, so I'm going to wrap it up here. Thanks for watching, you guys. See you in the next one. Peace.